This chapter is on Chapter 8, Part 1, Quantities in Chemical Reactions. At the completion of this chapter, you'll be able to perform stoichiometric mole-to-mole conversions and stoichiometric mass-to-mass conversions, and will understand what stoichiometry is about. Global warming is due to too much carbon dioxide in the atmosphere. The combustion of fossil fuels, such as octane, which are shown in the upper right circle in this diagram, produces water and carbon dioxide as products. Carbon dioxide is what is known as a greenhouse gas that is believed to be responsible for global warming. And the way this works is that carbon dioxide forms a shield around the Earth, shown in this picture here, that allows visible light to come in and heat to be trapped at the Earth's surface. Outgoing heat is then trapped and the Earth continues to warm up. Let's talk about the combustion of fossil fuels to produce carbon dioxide. Consider the combustion of octane, which is C8H18, and this is a component of gasoline. Right here is the shown the balanced chemical reaction for this. 2 molecules of octane combine with 25 molecules of oxygen gas to form 16 molecules of carbon dioxide and 18 molecules of water. This equation shows that 16 moles of carbon dioxide are produced for every 2 moles of octane burned. Since we know the world's annual fossil fuel consumption, we can estimate the world's annual CO2 production using the balanced chemical equation I just showed. This calculation shows that the world's annual CO2 production from fossil fuel combustion matches the measured annual atmospheric CO2 increase. And this implies that fossil fuel is responsible for the increase in carbon dioxide levels in our atmosphere. So what is stoichiometry? The numerical relationship between chemical quantities in a balanced chemical equation is called reaction stoichiometry. It tells us some things about products and reactants. We can predict the amounts of products that form in a chemical reaction based on the amount of reactants we know about. Or we can predict how many reactants we need to use to come up with a certain amount of product. We can predict how much of one reactant is required to completely react with another reactant to give us 100% yield in our reaction. So let's make it simpler and bring it down to what we can do when we're cooking in the kitchen. If we take 1 cup of flour and 2 eggs, then 1/2 teaspoon of baking powder, we know we can make 5 pancakes. Sounds kind of like a chemical reaction, doesn't it? So we know that there's a relationship between the number of eggs and the number of pancakes we can make. We can use 2 eggs to get 5 pancakes if we have enough of everything else. And so the ratio is shown in the bottom of 2 eggs to 5 pancakes. So you can make a ratio out of those relationships. So what if we have 8 eggs, assuming that we have enough of everything else to make pancakes? How many pancakes can we make? Well, if we take 2 eggs, which makes 5 pancakes, and multiply by 4, we would have 8 eggs and come up with 20 pancakes. Well, the same thing happens in a chemical reaction shown here down below. Here we see 3 molecules of hydrogen forming with 1 molecule of nitrogen gas to create ammonia, 2 moles. So let's talk about mole-to-mole conversion. In a balanced chemical reaction, we have a recipe, if you will, for how reactants combine to form products. This is the same reaction we just looked at and gives you the same kind of ratios that we saw when we were talking about pancakes. 3 moles of hydrogen and 1 mole of nitrogen gas equals 2 moles of ammonia gas, or in this case molecules. But we can express this relationship in moles like we see down below in the bottom equation. So if we have 3 moles of nitrogen and more than enough hydrogen, how many moles of ammonia gas can we make? Well, we know there's a relationship right here, shown here, when we put our solution map together, of 2 moles of ammonia to 1 mole of nitrogen. And we got that from the balanced equation. So let's say we have 3 moles of nitrogen to start off with. The solution's shown down below, times the ratio that we know about here, right here. So 3 moles of nitrogen and 2 moles of ammonia gas, and we've canceled out the moles of nitrogen, would equal to 6 moles of ammonia gas. So we have enough nitrogen to make 6 moles of nitrogen gas. What happens when we don't have enough oxygen to burn our octane efficiently? Here's that equation again. 2 moles of ethane, or not ethane, I'm sorry, 2 moles of octane, and 25 moles of oxygen give us 16 moles of carbon dioxide and 18 moles of water. If we have not enough oxygen, then we wind up coming up with pollutants. We don't get this same chemical reaction. We get carbon monoxide and ozone and all kinds of things. So back in 1990, there was an amendment made to make sure that according to the Clean Air Act, oil companies would put enough additives in gasoline to increase its oxygen content. They used MTBE, which is an abbreviation for methyl tertiary butyl ether, shown in this chemical formula here, right here. It was the additive of choice at that time, but it was not biodegradable and created all kinds of problems for spills at gasoline stations, motorboat problems in lakes, and underground storage tanks. So what have they replaced that with? Well, you guys might be familiar with ethanol because we see more and more of it all the time in our gasoline, and that's what gives us a little bit more oxygen. Originally it was expensive, but now it's becoming less expensive to add. So a chemical equation contains conversion factors between moles of reactants and moles of products. We are interested in relationships between the mass of reactants and the mass of products. The general outline for this type of calculation is given in this diagram below, where the mass of A goes to, you can convert to the moles of A by using molar mass relationships. And then with your equations from your balanced chemical reaction, you can make a ratio of how many moles of A go to moles of B and then convert to mass. So, what mass of carbon dioxide is emitted by an automobile per 5 times 10 to the second power grams of pure octane used? The balanced chemical equation gives us a relationship between moles of octane and moles of carbon dioxide. Before using that relationship, we must convert from grams to moles. So here we go. We know that with the molecular weight of octane, we get 114.3 grams of octane. So we can make this relationship of 1 mole of octane to 114.3 grams of octane. And then in order to take the numerator and denominator and cancel them, we can wind up doing the relationship between carbon dioxide and octane, which is 2 to 16, and then come up with the mass of carbon dioxide by using the ratio of the molecular weight of carbon dioxide and in 1 mole of carbon dioxide, which is 44.01 grams. So here's the math. We have 5 grams of octane, and we multiply by the 1 mole of octane to 114.3 grams of octane, canceling the grams of octane. Multiply by 16 moles of carbon dioxide to 2 moles of octane, cancel the moles of octane. and multiply by 44.01 grams of carbon dioxide per 1 mole of carbon dioxide. Cancel your moles of carbon dioxide, and what do you get but 1.5 times 10 to the third grams of carbon dioxide. So this is the end of the first part of Chapter 1, and we'll continue to use some of these relationships we've just developed in the next time that we meet to talk about stoichiometry further and to talk about heats of reaction. So see you then.